Hello everyone, welcome to this video. This presentation is entitled Impedance-based analysis of EMI filter and DC-DC converter interaction. In this video we will see first an introduction, then we will see how to do the analysis based on the impedances of the EMI filter and the DC-DC converter. And then we will study the three different cases that we have seen in previous videos. The case of the undamped EMI filter, the case of the modified compensator to solve the problem of instabilities, and lastly, the case of using a damped EMI filter also to avoid the unstable behavior of the converter. Along the video, we will see several LTS-based simulations to verify the different analyses. These are relevant videos related to this topic. Power electronics number 47. In this video, we studied the effect of the EMI filter on the dynamic response of DC-DC converters. Power electronics number 48, in which we study how to stabilize the DC-DC converter in closed loop, considering the effect of the EMI filter. And also because today we are going to do the analysis based on the impedances. These other two videos are also relevant. LTS-based number 21, 3 ways to obtain the input impedance of a DC-DC converter in open loop. And power electronics number 41, closed loop input impedance of a DC-DC converter. In previous video, Power Electronics 47, we talked about the effect of EMI filter on the dynamic response of DC-DC converters. So we know that if we have a DC-DC converter like the buck converter here, operating without EMI filter at the input, the current that we are injecting into the grid, here represented by this voltage source, is going to be discontinuous, and this creates a lot of noise in the grid. So we add an LC filter in order to have at the end, at the input, through the grid, a current that is going to be more or less as a DC current with low current ripple. Also, we saw that by adding this filter here, we are going to affect the dynamic response of the whole converter. And in some situations, the operation of the converter can become unstable. In the previous videos, we studied the effect of the EMI filter on the behavior of the DC-DC converter by obtaining the control to output transfer function of the DC-DC converter, including the EMI filter. But today we are going to use a different approach. We are going to use an impedance-based analysis. So we are going to consider that we have here the voltage corresponding to the grid, we have our EMI filter, and then we have our DC-DC converter operating in closed loop. So we are going to see the interaction here between the EMI filter and the DC-DC converter. So the input voltage source plus the EMI filter can be modeled with this equivalent circuit here. VF is the voltage, the equivalent voltage that we are going to have in a general situation. And CF is the equivalent impedance of the EMI filter. And on the side of the DC-DC converter, we can represent the converter by using the input impedance here, Ci. So we can calculate the voltage that we are going to have here at the interface using this simple expression here. The voltage Vx is this value, the ratio of these impedances, times the voltage Vf. We can consider this also as a transfer function, Gx, which is the voltage at the interface over the voltage Vf, and it is equal to this expression here. So in order to analyze the stability of this configuration, the EMI filter and the DC-DC converters, we have to analyze if this transfer function is going to be also stable or not. So the important point at the end is if the roots of the expression here in the denominator are going to be on the right half plane of the imaginary and real plane. So let's investigate the different situations that we have seen also in previous videos. So to do the analysis, we first need to obtain the expressions of the impedances CF and Ci. In the case of CF, here we have the EMI filter with the inductor and the capacitor. So CF is the impedance that we see in this direction. We can obtain the impedance from this circuit. We make null, of course, the input voltage, and then we obtain this expression, and from it we get finally this equation here. So we can see that CF has to conjugate poles on the imaginary axis, because this makes more difficult to plot and to understand the Nyquist plots and both diagrams. We are going to do a little trick to move the poles a little bit out of the imaginary axis, but having practically the same behavior of the EMI filter. The trick consists in adding this parallel resistance here, RD. So this resistance is going to be high enough, so at the end we are going to have more or less the same behavior as when we have LF and CF only. But with this we are going to avoid having two poles exactly on the imaginary axis. So if we studied the value of ZF here, then we can calculate the expression and we obtain finally this equation here. So in order that the value of ARD is negligible, what we need is that the value of RD must be much higher than the characteristic impedance of the circuit, which is given by the square root of LF over CF, as we know. For example, in the cases that we are going to see, we are going to use 100 microhenries for LF and 10 microfarads for CF. So the characteristic impedance is 3.2 ohms. So let's choose, for example, RD equal to 100 ohm. And the other impedance that we need is the impedance of our converter, in this case the buck converter operating in closed loop. We have seen how to do this in this previous video, Power Electronics number 41. Here we have the equations, the equivalent circuit, and this is the expression of the input impedance of the converter operating in closed loop, where here in blue we have the expression corresponding to the compensator. So with this we have everything. We have the impedance on the side of the EMI filter, and we have the impedance on the side of the DC-DC converter, so we can proceed with our stability analysis. This is the converter that we are using. It's exactly the same that we have used in previous videos. We have our buck converter with all the values that we are showing here operating in closed loop. This is the expression of the first compensator that we have implemented when we were not including the EMI filter, and here we have the values and so on. Now let's remember what we have to do. This is the expression of our system, And what we have to determine is if this system is stable or not. By determining if the zeros of the expression here, the characteristic equation here in the denominator, are situated on the right half plane. As we know, at the end, the important expression is this factor here that we are going to call Fs. And we can calculate the value of Fs using the impedances that we have obtained before. For the EMI filter, we obtain Cf, which is this expression here, and for the converter, we obtained Ci, which is this other expression here. Now it's important to note the following. First, Cf does not add any pole on the right half plane, as we have seen, just to conjugate poles close to the imaginary axis, but on the left half plane. And also 1 over Zi does not have any right half plane either, because otherwise the converter wouldn't be stable in closed loop without EMI filter. In that case, the input current would not converge, and we have seen that the converter is stable without EMI filter. So why this is important? This is important because therefore we can use the simplified Nyquist criterion and the body diagram criterion to evaluate the stability of the system. And now let's analyze the first example. This is the case of the unstable system in which we have our buck converter operating in closed loop with this compensator here with these values, and then we added the EMI filter with these two values for the inductance and the capacitance. And then when we simulated the converter, we saw that we have this unstable behavior. We studied this in this previous video, Power Electronics 47. Now we are going to analyze this case from the point of view of the impedances. So here we have this WinPython script in which we have all the values, all the parameters of the converter. We have calculated here the expression corresponding to Zf, and here the expression corresponding to Zi. And this is also the function f. Now if we do the plotting using this command here, we obtain this body plot corresponding to the magnitude and the phase of the function f. So we can see how when we reach the value of minus 180 degrees for the phase, we are having a magnitude of f much higher than 1, higher than 0 dBs here. So we have clearly an unstable behavior. We can also do the plotting of the Nyquist diagram using these commands here, and then we obtain this diagram corresponding to the function f on the s-plane, and then we can see how the point minus 1, 0 is encircled by the Nyquist diagram. So clearly we get also an unstable behavior. So this is another way of proving that we have an unstable behavior when we add a pure LFCF EMI filter. Now let's analyze the first solution that we saw to solve this issue is to modify the compensator. We studied how to do this in this video, Power Electronics number 48, and what we did is to modify our compensator, adding this capacitor here and then changing the different values of the components of the compensator. And with this we can see here how we get unstable behavior for the output voltage. Here we have a step on the load, and then we have a transient. This is the change of the output of the compensator, and this is the output voltage reaching again the value of 5 volts. So let's analyze this case using the impedances of the EMI filter and the converter. So here we have the WinPython script again. In this case, we have the same value for the impedance of the filter, also the same value of the impedance of the DC-DC converter, but changing the expression of the compensator, which is this one now with the values shown here. And then if we do the plotting, we obtain this Bode diagram, in which if we look at the value at minus 180 degrees of the magnitude of the function f, we can see that is lower than 0 dBs. So we have a stable system. And to be sure about this, because here we have a cross over 0 dBs and then another cross over 0 dBs, so this is kind of a strange Bode plot, we can do the plotting of the Nyquist diagram, and then we obtain this diagram here. This point is the minus 1, 0 point, and if we do a zoom here, we can see that is out of the diagram, so we are not encircling the point minus 1, 0, so we have a stable system. The other solution that we studied in this previous video, Power Electronics 48, is to dump the EMI filter. So we added this capacitor here in series with this resistance, and with this we are dumping the filter so we can get a stable system again, and also we can improve the dynamics of the converter. So with this we can use exactly the same compensator as we have designed, and then we saw how we get also a stable response for the converter. So again, we are going to study this from the point of view of the impedances of the filter and the converter. In this case of the damped EMI filter, we have this diagram for the filter, so we can obtain also the impedance CF as shown here using this expression. And also we have seen that in the design of the filter, this is the condition that we need, because we need that the impedance of this capacitor here, CF1, must be much lower than the series resistance RF at the resonant frequency of the filter. So with this, we saw in this previous video how to calculate the different values for a cutoff frequency of 5 kHz and a value of RF equal to 1 ohm. We get that CF1 has to be much greater than approximately 32 microfarads, and we selected 300 microfarads. So these are the final values for our filter. And here we have the plotting again. This is the script with the values of the impedances and the function f with all the parameters that we have seen in previous slide. And then this is the Bode plot corresponding to f. So we can see that f is always lower than 0 dBs. So when we get 100 minus 180 degrees, then we get a value lower than 0 dB, so this is clearly a stable system. If we do the Nyquist diagram, then we can see also that here is the point minus 1, 0, and the diagram is much smaller than 1, so we can see that the point is out of the diagram, and this is again clearly a stable system. So this is another way to look at the stability of our system. We can compare the impedances CF and CI, and if the ratio of these two impedances, the magnitude of this ratio, is lower than 1 at all frequencies, then we can assure that our system is going to be stable. We can calculate in dBs this factor by doing the magnitude of ZF in dBs minus the magnitude of CI in dBs. And if this is always lower than 0 dBs, then we can assure that our system is going to be stable. For example, here we have CI, we have ZF, and then we have the value of F, which is ZF minus ZI. In this case that we have seen before, in the last case, we can see that F is always below 0 dBs, so our system is going to be stable. And finally, let's play a little bit. We saw when we studied oscillators in analog electronics that if in a system we design the system to have 0 dBs at minus 180 degrees exactly, our system becomes an oscillator. So we can play with the value of RF, as shown here, in order to have this situation. So for a value of RF equal to 3.7 ohms, we get this situation in which we have exactly 0 dBs and minus 180 degrees. Also, on the Nyquist diagram, we can see that the point here, minus 10, is exactly on the Nyquist diagram. And also note that the frequency at which we have this situation is 4.6 kilohertz. So what we have just done is to create an oscillator at 4.6 kilohertz. So let's do a simulation in LTS-SPICE to see what is the behavior of our converter in this situation. So here we have our LTS-SPICE circuit. We have only changed the value of this series resistance in the filter to 3.7 ohms. And here we have the results that we have obtained. In green, we have the output of the compensator. This is the voltage at the interface between the filter and the converter. This is the voltage Vx here, and this is the output voltage in blue. So we can see how the voltage Vx is almost a sinusoidal waveform. The frequency is 4.4 kilohertz, very similar to the value that we have just calculated. And it is not a pure sinusoidal waveform because, as we can see here, we are getting the saturation at the output of the compensator. If we play with the different parameters here in our circuit, for example, decreasing the reference voltage a little bit, then we can get an oscillating circuit in which the voltage is going to be almost a sinusoidal waveform because the output of the compensator is going to remain at all times within the linear region. Well, this concludes this presentation today. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.